Hello everybody, in Module 5, I discussed real effects of accounting disclosures. Module 5 has 6 lessons. Today we focus on Lesson 4, real effects of measurement noise. The discussion is based on Canoli et al. 2005 JAR paper. The paper provides a justification for why measurement noise might be desirable, which is counterintuitive because we usually think about measurement noise as not good. They show this in a model with real effects and multiple frictions. The big picture intuition is based on a basic theorem of welfare economics. An economy with multiple frictions, remove just the one friction may not necessarily make the economy better off because it may exacerbate other frictions. Now let's look at the setup. The manager privately observes theta and chooses the amount of investment to maximize theta k minus 1/2 k squared plus the expected value of gamma theta k based on whatever market information is. We think about this objective function as firm's investment generating a current cash flow of theta k minus 1/2 k squared and future cash flow of gamma theta k. The market perceives theta to be normally distributed with mean mu and variance sigma theta squared, and k might be measured with noise. Again, this is a typical real effects model. There is information asymmetry between the manager and the market, and the manager cares about short-term prices. There are two frictions in this economy: information asymmetry about theta and measurement noise about investment. The first best means that neither friction is present, which means theta and k are publicly observed. So the manager is going to choose k to maximize theta k minus 1/2 k squared plus gamma theta k. First order condition results in the first best investment schedule to be 1 plus gamma times theta. Now let's look at some second best benchmarks, which means one friction is present. The first benchmark, theta is known, but k is measured with noise. The market does not observe k, it observes some noisy measure of k, s. The market is going to set price based on s and theta. And in equilibrium, the manager is going to choose k as a function of theta to maximize the manager's payoff function. And the market is going to set the price equal to expected future cash flow conditional on s. The result is quite striking. We can see here the optimal investment only maximizes short-term price. So there will be severe underinvestment. Instead of investing 1 plus gamma theta, the manager only invests theta. Why is that? The intuition is similar to what we discussed in lesson 2 of this module. When theta is known, investor can step into the manager's shoes and figure out the manager's investment schedule, k theta. In this case, s has no information content. Investor is going to attribute any difference between s and k theta to noise. In this case, phi s theta is based on investor's conjecture of k, and that's completely independent of manager's actual choice. So manager would take phi s theta as a constant when choosing k, resulting in managers only choosing k to maximize the short-term cash flow. Now let's look at the second best benchmark. This is the case when theta is not known, but k is measured perfectly. So this reminds you of the typical adverse selection models when theta is private information. And so in this case, we have a signal equilibrium. Manager uses the investment to signal private information. And again, as in any signal equilibrium or any adverse selection models, you have to ensure that it is incentive compatible for managers observing theta to choose this particular investment schedule, k theta, other than mimicking the investment schedule of some other type, theta prime. Investors, they would conjecture managers' investment schedule. And this conjecture would be conferred in equilibrium. The conjecture has to be consistent. So what investors is going to do is they're going to observe k, and they're going to back out theta from k. And this backing out is denoted as ik. So again, the manager chooses k to maximize the manager's payoff. The market pricing now only depends on k because the market cannot observe theta. But the market is going to back out theta from k and use that to calculate the expected future cash flow. You can use guess and verify approach for this, or you can use mechanism design as we briefly mentioned in the previous 2 lessons. Now let's use guess and verify. Let's guess the investment is B theta for some B that is bigger than 0, that will eventually be determined equilibrium. And in this case, then, if we conjecture that K is B theta, then whenever we observe K, we divide K by B. That's our inference of theta. And so we insert that into the objective function of the manager. We take first all the condition. We would get an expression of K. And then matching coefficients, we're going to get B equals 1 plus 2 gamma. So in this case, that will be overinvestment because in the first best, the coefficient is 1 plus gamma. And the intuition is similar to a typical signaling model. Firm is going to overinvest to signal high theta and to prevent firms with low theta to mimic. What if we have both frictions? We have both private information of theta from the manager and measurement noise. Remember, if we only have private information, we have signal equilibrium. Now, when we have measurement noise as well, we have a noisy signal equilibrium. So in this case, investors, they're still going to conjecture manager's investment schedule, K theta. They know that the manager observes theta. So they know that the manager's investment is going to be based on theta. So they're going to make that conjecture. But they cannot observe K. They can only observe K with noise, which is why we call this a noisy signaling equilibrium. So in this case, investors, they're going to use Bayes' rule to try to figure out the distribution of theta given S and given the investor's conjecture about manager's investment schedule. You can use Bayes' rule to figure out theta because theta is exogenous variable. Again, we can use guess and verify in this simple setting. In more complicated settings, then we need more advanced techniques. We guess that, again, the investment is a linear function of theta. It's A plus B theta for some A and B that is going to be determined in equilibrium. Then in this case, we can calculate the market's pricing function of the firm's future cash flow. And in this case, it involves Bayesian updating expected value of theta conditional S, and expected value of theta squared conditional S, and eventually it becomes a quadratic function of S. And we're able to, based on Bayesian updating, get those coefficients. And then we can match coefficients. That results in 2 equations for the 2 unknowns, A and B. And we can show that B is always between 1 and 1 plus 2 gamma, which means that the sensitivity of investment to theta lies in between the value between the 2 second best scenarios. And we can show that if B is equal to 1 plus gamma, then we can achieve first best. To achieve this, we can show that it needs mu equals 0 and also sigma epsilon squared to be positive. So some optimal level of reporting noise can restore investment to first best. Once we have this, we can have some comparative statics of the optimal amount of reporting noise. And we can show that the optimal amount of reporting noise should be higher if sigma theta squared is higher. And it would be higher if gamma is higher. And here's the intuition. Sigma theta squared represents the information asymmetry between the manager and the markets, because the manager observes theta, and the market perceives theta to be normally distributed with variance sigma theta squared. And information asymmetry is higher, that results in more severe overinvestment. Because we know that measurement noise results in underinvestment, so we need more measurement noise, more underinvestment to dampen overinvestment. And when gamma is higher, the future cash flow is more important to the pricing. And the future cash flow also depends on theta. So again, the signaling incentive becomes higher. And therefore, we need more measurement noise. We need more underinvestment to dampen the overinvestment incentive. Therefore, the implications are that we should tolerate more measurement noise, more investment precision, or maybe sometimes not measuring investments when the information asymmetry between the market and the firm is higher. when gamma is higher, which means when growth option is more important to the firm. Gao and Liang also has such prediction, but their prediction is based on feedback effects. And here the prediction is based on the manager being more informed, and it's based on the real effects. And also when investment is less costly. This is another comparative static that we didn't touch in this simplified setting. In general, you want more investment precision when the signaling incentive and therefore the overinvestment incentives are larger. To conclude, when an economy has multiple frictions, you remove one friction may not necessarily make the economy better off. And in this specific setting, managerial private information may result in firm overinvest because of signaling. And in this case, we may need more noise in measurement of investment so that we have underinvestment to counter the overinvestment. So in this case, some amount of measurement noise is beneficial. If you want to test your understanding of this lesson, a review quiz can be provided at the slides